Swayam Prabha. Digital India. Educated India.
Today we will extend the torsional vibration using finite element method. Today especially we will be dealing with the geared system, and in previous lectures we have covered the geared pair using either equivalence system approach or even with the transfer matrix method. So, today we will extend the gear element, we will develop the gear element using finite element method, and we will see that how this gear element can be used for either geared system or for even branch system. And in this particular torsional vibration of the geared system, we will extend even if there is a flexibility at the gear tooth, how it can be incorporated in the finite element formulation. So, basically this is the overall overview of the lecture, in which we will be developing we will be doing the torsional vibration of geared and branch system using finite element method. We will do the development of the gear element, and we will see if gear contact is having flexibility that can how we can able to incorporate in the gear element. So, let us take a gear system. This is a flywheel and this is a shaft, and we have one gear and is connected to another gear, and we have another flywheel. So, these flywheel are having a large polar moment of inertia. These gears can have polar moment of inertia, but they will be comparatively smaller as compared to the flywheel. So, we will try to develop a gear element so that for this particular gear, so we will be considering this particular gear pair, and because the angular displacement of the second gear is related with the first gear with the gear ratio. So, when we will be discretizing this particular system, let us say if we are discretizing the upper shaft with the gear as element 1 and the second shaft with gear and flywheel as second element, and at various positions, like this is a node 1, node 2, node 3, node 4. So, we will see that at each node we need to assign one angular displacements, and there are 4 angular displacements, but out of these 4 these 2 are related by gear ratio. So, we will try to eliminate or replace the angular displacement at node 3 by the angular displacement at node 2, and that will give us the elemental equation. So, let us see how we can able to develop this element equation for the gear pair in the subsequent slide. So, we have a gear pair and they have a rotational speed omega 1, and this will be having opposite to that, but this angular speed is related with the previous one with the gear ratio. I am taking the torsional oscillation of this. These are the nominal speed. These are the torsional oscillation angular displacement. I am taking both as counterclockwise direction as positive convention, and the sign negative sign will take care of their direction, because this has to rotate opposite to this, but according to this sign convention then they will be related with the negative sign. So, the gear 1 and gear 2 they have angular displacement, these two, and these two are related by the gear ratio. Now, we will see the moment of inertia, polar moment of inertia, mass moment of inertia of this gear corresponding to the angular displacement or the angular speed of the first gear. We have already seen that this can be obtained using equivalent system like this. So, we have first gear which is having polar moment of inertia this one, and we have second gear and polar moment of inertia is this, and these two angular displacements, as we have seen, are related. So, at this position corresponding to the speed of the input shaft, let us say this is the input shaft, this moment of inertia can be replaced by equivalent moment of inertia corresponding to the angular displacement at the this node. So, you can able to see this is the angular this is the polar moment of inertia of this gear, and this is the equivalent polar moment of inertia of this second gear corresponding to the angular displacement here. This is the gear ratio. So, this is the total inertia of both the gears would be at node at this node position, and this can be replaced can be written in this form corresponding to the angular displacement at 1. This is corresponding to the angular displacement at gear here, and this is the second is corresponding to the, if we have this is IP2. So, this particular angular displacement is this one, which is a flywheel. Now, because if we expand this equation, I will get back this one. So, this 0 0 entry is not making any difference as compared to the what we got in the equivalent polar moment of inertia of both the gear. Now, we will see the strain energy stored in the shaft. So, this particular shaft is the second shaft, this shaft, and we are trying to see what is the strain energy stored in this, and what is the work done by the torque at the ends. So, you can able to see this is the shaft at this, let us say is a node 1, this is node 2, corresponding to this I am assuming phi z1 and phi z2 as the angular displacement, but this phi z1 is which is at the gear 2 is related with the angular displacement at gear 1 by gear ratio and negative sign, because the sign convention we have chosen. So, you can able to see that now the angular displacement in the second shaft where the gear 2 is there, we will be representing the angular displacement corresponding to the gear 1, and here this is the angular displacement corresponding to the flywheel 2. So, here we are not referring to the first shaft speed. Here whatever the angular displacement of the second gear is flywheel is taking place, that itself we are taking it. So, as such in finite element method we are not converting the whole shaft into the equivalent shaft system. So, this is the original stiffness of the second shaft. So, now the strain energy stored in the shaft will be the torsional stiffness and the relative twist between the two ends of the shaft. So, phi z2 minus phi z1. Now, phi z1 we can able to replace with the gear 1 angular displacement. So, this expression we can substitute here. So, this will become positive. So, this is this term and this is phi z2. Similarly, the work done by these two torques, the reaction torques, because of these angular displacements will be given by this, and this angular displacement again we can able to replace with respect to the gear 1 angular displacement. So, now we got the energy stored in the system. Now, we can apply Rayleigh-Ritz method. Basically, it minimizes the energy, these two energy. So, we can able to see we are minimizing these two energy with respect to the first with respect to the angular displacement corresponding to the gear 1. So, if we differentiate this, can able to see the first one, if we differentiate del u 1 by del phi z g 1. So, we will get 2 will get cancelled and phi z g 1 by n plus phi z 2, and then once we again differentiate we will get this. Similarly, we can able to differentiate w 1 with respect to phi z g 1. So, only one term is there. So, we will get T 1 by n. So, these two expressions are here and they can be rearranged like this. I am taking the torque in right side, and you can able to see we are minimizing the energy. So, we are after partial differentiation of this, we are equating this term equal to 0, and now I am rearranging this equation in this form where torque I am taking this side, phi z g 1 and phi z 2 terms are in the left side. Similarly, we can minimize this energy with respect to phi z 2, second variable of the element, and once we differentiate we will get this expression. This is corresponding to the strain energy and this is corresponding to the work done, and this again can be rearranged in this form in which we are putting the torque in the other side. Now, this equation and the previous equation, this equation we can combine. So, these are the two equations which we got it. Now, I am combining these two equations in a matrix form. So, you can able to see this is a vector and these 4 elements are coming in the matrix, and right hand side is a vector containing these 2 terms. So, this equation we got it from the strain energy and the work done. Earlier we got the term corresponding to the inertia, that was this one. So, that we can add it here to get the overall elemental equation for the gear pair. So, this is the inertia term which we obtained earlier, and this is the stiffness term, and this is the reactive torque at the end of the shaft. So, this is the gear element equation, and this is a very important relation. Using this we can able to analyze the branch system and geared system very easily. Now, once we have developed the gear element, we have seen that we got with the gear element 1 the mass matrix and the stiffness matrix, which are having a different form as compared to the conventional finite element of the for the torsional oscillation, torsional vibration of a simple shaft element, because now gear ratios are also appearing. Now, with this gear element, let us see how we can able to analyze a simple geared system. So, we are taking a simple gear rotor system in which we have a gear pair like this. We have 2 flywheels at the end, and this 2 shafts A and B are connected by a gear pair. Various property of the system like diameter of the shaft A, length of the shaft A, Also for shaft B, they have different dimensions, so they are given. Modulus of rigidity of both the shafts are given. Even polar moment of inertia of the two flywheel on shaft A and B are given, and even now we are considering the polar moment of inertia, mass moment of inertia of the gears also. So, gear A and B, they have some polar mass moment of inertia. Now, with this we can able to obtain second polar moment of inertia using this relations, because we know the diameter of the shaft. This will be using in the elemental equation. So, now you can able to see we have divided this whole system into two elements. So, this is one element in which node 1 and 2 are there, and this is the element 1. Similarly, this is the second element in which this is node 3 and 4. So, basically we have divided this into two parts, element 1 which is coming here, node 1 and 2, and second element is like this, in which we have node 3 and 4. Now, once we have divided into two elements, we can able to like this, we can able to write the elemental equation for each of them, and then we can able to see how they can be combined. So, some more property like the stiffness we can able to calculate of the shaft 1 and 2 using these relations for the data given in the problem. So, now this is the elemental equation for element 1. So, in element 1 we had node 1 and 2. So, I am again drawing that element 1, node 1 and 2. So, correspondingly we will be having the phi z1 and phi z2. Here we are not considering the shaft inertia property, only whatever the flywheel and the gear polar moment of inertia are there, that we have considered. So, in this particular case we have not considered the shaft inertia, only the whatever the lump masses are there at the end that has been considered. This is the stiffness matrix, conventional stiffness matrix, and this is the same vector as this. Only thing is here this is a displacement, this is a inertia, and these are the reaction torque at node 1 and 2, T1 and T2. For gear element 2, for the element 2 we have node 3 and 4. So, in this, if we want to write exactly the same elemental equation for this, we will be having phi z3 and phi z4, and these are the gear and flywheel which are there at node 3 and 4, and this is the stiffness matrix, and these are the reaction torque at the ends. Till now we have not used the gear element because now you can see that node 2 and 3 angular displacements are related. So, as such we should eliminate the this angular displacement at node 3 with the node 2, because we know they are related with the gear ratio like this. If you want to do that, so obviously we need to convert this elemental equation according to the geared element which we developed. So, you can able to see this particular moment of inertia, mass moment of inertia, which is there at gear node 3, need to be divided by square of the gear ratio. This we need not divide, because this particular angular displacement is same as that of the node 4. This is not related with the gear ratio. So, we are keeping this as it is. Here if we see this term will be divided by gear ratio square, and this 2 by gear ratio, as if we refer back the elemental equation this was divided by n square, the gear polar mass moment of inertia, and these stiffness terms are divided by gear ratio square and gear ratio. This will not be changing, and here also the torque will be divided by gear ratio. So, we have divided that also by gear ratio. Now, we will be assembling this equation and this equation, and you can able to see in this only 3 variables are there corresponding to node 1, 2 and 4. So, this is the assembled equation, because now we have enough background how to assemble such equation. So, you can able to see that 3 variables are there, and the first 2 are corresponding to the element 1 and these 2 are corresponding to second element. Similarly, here this is corresponding to the second element and these 4 are from the first element, and these are the torque which are this is at the common node, that is node 2, and at junction we know this torque will cancel because the reactive torque, once we assemble these elements, they should cancel at the junction. And apart from this, because the ends of the both the shafts are free, so at node 1 and 4 there will not be torque because they are free end where the flywheels are there. So, corresponding torques will be 0. So, this will be 0, this will be 0, this anyway 0 because of this is at the junction point. Now, once these are 0, this equation we can able to write in this form after simplifying. In this particular case, we have replaced this with, for simple harmonic motion, as this minus of this. So, this is minus of omega n square, and this displacement vector I have taken outside. So, basically this, if we take the determinant of this equal to 0, we will get a polynomial, and that will give us the natural frequency of the system, because this is a homogeneous equation. And alternately, what we can able to do, we can develop the eigenvalue as we discussed in the previous lecture. So, we will take the inverse of the mass matrix and multiply with K matrix, and if we obtain the eigenvalue of this, from this we can able to get the natural frequency from eigenvalues, and eigenvector will give us the how various nodes are having relative displacements. So, this is corresponding to the first natural frequency. You can able to see the node 1 and 2 are having same displacement. This is corresponding to node 4, which is because of the gear ratio become half. Otherwise, as such, this is a rigid body mode, but these are flexible modes, and so we have 3 natural frequency. Out of that, 2 are flexible mode and 1 is rigid body mode. Only this particular, this is corresponding to the 4, and this is phi z1 and phi z2. Phi z3 is related with this. So, if we divide this by gear ratio, we can get the phi z3 displacement. Now, we will take up another example for a branch system. The same element equation for gear pair can be used for analyzing the branch system also. So, let us see that particular example. So, basically this is a branch system in which one flywheel is here and we have shaft, and we are having 2 shafts connected with this by 2 gear. So, gear B is connected to gear C and D, and which is giving power to the flywheel E and F. For simplicity of illustration, we have not taken intermediate disc, but that also can be taken. So, basically various property of these discs are given. For flywheel, we have this property, and gear also have polar moment of inertia, and they are not negligible. Whereas gear ratio, like for between gear B and C is 3, between gear B and D is 4, and whereas the lengths of the shafts are given, diameter is also given, and shaft modulus of rigidity is also given. So, with this property, now you can able to see, if we want to analyze this, we need to take this particular branch as element 1, this we can take as element 2, and third branch as element 3. We can able to write the elemental equation for each of them, and then we can assemble them for applying the boundary conditions. So, let us see the first element, which is branch A. Here we have one flywheel, and this is corresponding to the gear. So, as such, in this whatever the torsional elemental equation we develop will be valid for this. So, you can able to see these are the lump masses. Here again we have not considered the inertia of the shaft, only masses which are lumped at the ends are considered. So, they are coming at the diagonal, and these are the angular displacement corresponding to node this node A and B, and this is the stiffness of the shaft element 1, and these are the reaction torque at end A and B. Similarly, we can able to write elemental equation for element 2, but here we are considering, instead of phi ZC, we are considering the phi ZB. That is a because this gear C and B are connected by, and they are related by gear ratio. So, directly we are replacing that particular angular displacement. This will remain same as of the end E. So, you can able to see this we need to divide by gear ratio square. Similarly, in the stiffness matrix, this term will be divided by gear ratio square, and off diagonal terms will be divided by gear ratio only, and these will be minus, and this torque also we need to divide by gear ratio as we have seen earlier, but this will be unaffected. Similarly, we can able to develop elemental equation for third branch, that is, and this is the element 3. Here we should have angular displacement phi z d, but we have replaced that by phi z b, the gear which is driving this. So, we need to use the gear ratio B to D here in the inertia term, also in the stiffness term, they will also be negative here. So, you can able to see the torque also we need to divide by the gear ratio. Now, we can combine these. You can able to see we will be having only 4 angular displacement at node A, B, E, F. At the junction point C and D, gear displacements we have already replaced by the gear ratio, gear displacement at B. So, you can able to see that because of that during the assembly at this position we have equivalent polar moment of inertia of gear C and D also added to the gear B polar moment of inertia. Similarly, this is the stiffness term. You can able to see the first 4 terms are corresponding to element 1, then these terms are corresponding to second branch, and these are corresponding to third branch. And at junction point these torque will cancel each other, and now in this particular case also, and A, E and F, they are free ends. So, torque at those locations will be 0. So, we will be having these torques also as 0, and Now you can able to see in the right hand side all terms are 0. So this equation can be simplified in this form: k minus this m. This is conventionally we have been doing this to converting the for free vibration this equation of motion in this particular form. So if we take the determinant of this equal to 0, we can get the frequency equation, or we can go for the eigenvalue problem, in which we can this d in this particular case is defined as inverse of m into k. So if we obtain the eigenvalue of d, we can able to get the natural frequency and the mode shape also. So for given data, various stiffness terms we can able to calculate, and this is the stiffness matrix and this is the mass matrix corresponding to the various property of the branch system. And if we solve the eigenvalue problem, we will get 4 natural frequencies. One of them is 0 because this free and conditions are there. So we expect one rigid body mode, but these are flexible modes. Even we can able to obtain the eigenvectors, and we have drawn this. So basically this is a branch 1, and so this is corresponding to element 1, is corresponding to element 2, is corresponding to element 3. This is the position where the gear is connected. So for a unit, this is for 0 natural frequency. So we expect a rigid body mode. So node 1 and 2, or node A and B, will be having same displacement 1. We expect this to have same displacement, but because of the gear ratio, this will be divided, 1 will be divided by 2. So this is 3. Gear ratio is we have 2 sets of gear ratio. So one is the 3, another is a 4. So you can able to see that the difference. So this is 1 by 3. This is nothing but 1 by 3, or this one is 1 by 3, and this is 1 by 4. So this is a gear ratio 3 and gear ratio 4. So you can able to see that whole the second element and third element are having same. As such, there is no relative twist between the ends. Similarly, we can able to plot the mode shape for flexible mode, that is second mode. So we can able to see this is now they have relative twist at end A and B. C and D will be 1 by 3 and 1 by 4th times of this particular height from here to here, because they are very close. So it looks at the same point, but they are not at the same point. Then and E and F will be having different displacement, so they can be connected. So this is the mode shape corresponding to this natural frequency, and this is the point where the gears are connected to each other. Similarly, other modes can be plotted. You can able to see their relative positions are changing. Here, because this amplitude is very less, so C, D appears to be at the same position, but they are not at the same position. Similarly, this is the fourth mode. Here now they are distinct. You can able to see now B is having opposite motion as compared to A, and now we have when we are dividing by 1 by 3 of this, C is coming here, and 1 by 4, then we are getting a D point here, and these are the other angular displacement and E and F. So this is the mode shape corresponding to the 4th natural frequency, which is flexible mode. Now we will take the case when the gears pair, when the two teeth, when they are in contact, because at that point we have direct contact between two teeth, and generally in gears we have a line contact, but when it is transmitting power, that particular line contact becomes area contact, and that particular stresses is governed by the Hertzian stress theory. Generally they are nonlinear in nature. that is the force and deformation relations are nonlinear in nature, but this particular case we are considering the linear stiffness at the contact point, and if there is a flexibility which is linear, how we can able to develop the governing equation for such gear pair, we will try to illustrate and we will try to obtain the equation of motion for such cases. So, in this particular case we are taking basically this kind of gear pair. You can able to see this is gear 1 and gear 2, these are flywheel, these are two flywheel, and in between the gear pair we are considering the flexibility due to the contact between two teeth, and that we can able to model like this. So, this is the pitch circle of the gear 1 and this of gear 2, and whatever the flexibility is there between the gear 2 during the contact, we are representing that as a linear spring. So, this is basically a linear spring, that means the extension or compression of this would take place during the motion, because these two are having oscillation, the torsional oscillations like this, and because of this you can able to expect that this particular spring will get extension or compression depending upon the relative angular displacements of these, and that will not only will depend upon their relative twist, but also the diameter of this pitch diameter of the gears. So, if pitch diameter is d1 and d2, then that particular extension whatever there will be governed by this diameters also. So, now let us see how we can able to analyze such system. So, I am first considering the first flywheel which is here, this particular flywheel, and I am trying to attach phi z1 is the angular displacement of this, phi z2 is angular displacement of this, phi z3 is angular displacement of this, phi z4 is angular displacement of this. Now, we can able to see that these two angular displacements are as such not related with the gear ratio, because now there is a flexible element in between this. So, basically these two are now independent angular displacements. So, in this particular case, if I am considering the angular displacement of this as positive in this direction, there will be torque from the shaft, reaction torque, which will be coming, which will be given as this. Now, you can able to see this is the only torque which is acting on this. So, using Newton's law, we can able to equate this torque which will be in the opposite direction to the displacement to the inertia. So, this is one of the equation of motion. Similarly, we can able to write the for gear 1, that is IP2. So, in this particular case, again the displacement direction is this positive direction. This torque will act in opposite direction to the previous one here. This torque will be acting here, and apart from this, there is a flexibility of the linear spring. So, for that case, you can able to see this is the gear 1 having radius d1 by 2, and this kg is the stiffness of the linear spring, and relative extension of the spring will be phi z2 minus d2 by 2 phi z3. So, relative extension of the spring will be, if we go back here, you can see relative extension of this will be how much angular displacement of this is taking place and how much angular displacement of this is taking place, and this diameter will give basically what is the actual extension of the spring of this end and this end. So, that is why we have used diameter there, so that we can able to get the actual extension. So, basically within the bracket term is actual extension of the spring at the contact point. So, this particular force, this particular torque, this is the force, and the torque will be again if we divide multiply by d1 by 2. So, this will give us the torque which will be acting on the gear 1. So, this is the force of the linear spring into d1 by 2 will give the torque. So, this particular torque will be acting opposite to the, so this torque will be acting opposite to the angular displacement, and this free body diagram of this we have written here. So, you can able to see this is the governing equation, this is the torque which is in this direction, positive direction. This particular torque is opposite to the angular displacement, should be equal to the inertia of this gear 2. So, once we obtain this, we can able to obtain the free body diagram of the second gear, that is having IP3. In this particular case also I am taking the angular displacement downward as positive direction. The torque from the linear spring will be given by this. So, you can able to see this is the force and this is the, now we can able to write the free body diagram for the second gear having polar moment of inertia of IP3. We are taking the angular displacement direction positive in the downward direction. From the linear spring at the contact point, we will get this particular torque. This is basically first, this term is force. Now, for torque we need to now multiply by d2 by 2. Earlier we multiplied by the d1 by 2, now we need to multiply by d2 by 2. And then from the second shaft, that means we have taken care of this, but this shaft is connected with this second gear. So, this will also give the reaction torque to this, because there will be relative twist between these two ends of the shaft. So, this will be opposite to the displacement. So, KT2 phi Z3 minus phi Z4. So, this is reaction torque from the shaft, this is reaction torque from the contact point linear spring, and you can able to see now this is the equation for this opposite to the angular displacement, this is in same direction as the angular displacement, should be equal to the inertia. So, this is the third equation of motion. Then the last disk having IP4, in this only one torque will be acting, and that will be in the value of the torque will be this, but direction will be opposite, but this case they will be in the same direction. So, this is the torque equilibrium of this particular flywheel. So, this is the fourth equation. So, basically all this equation, first equation, second equation, third equation and fourth equation are the governing equation of this particular whole system. They can be combined in the matrix form like this. So, you can able to see this is the mass matrix, this is the stiffness matrix. A solution of such system we have already done earlier. So, I will not illustrate the solution of this, but how the equation of motion can be obtained I have illustrated here using the Newton's law. Now, the same problem we will see using the transfer matrix method. So, in transfer matrix method we need to, let us say this is station 0, station 1, station 2, station 3. So, we have 4 stations from 0 to 3. Now we can able to see I have tilted the same thing, and here we have 0 station, 1 station, 2 station and 3 station. Now between station 1 and 2 we can able to write the state vector. So right of station 1 and station 0 is related with point matrix, field matrix and again point matrix. So this we already conversant with how to relate the state vector at two ends of this. Similarly, at the right of 3 and right of 2 we can able to relate right of 3 and left of 2 we can able to relate using this, and in between the right of 1 and left of 2, let us say we have this relation where F is the field matrix corresponding to the linear spring. Now we need to develop this one, others are we know. So now we will see how we can able to develop the field matrix for that linear spring corresponding to the flexibility of the gear pair. So this is the linear spring having stiffness this. Now at two ends we have the linear displacement these, because this angular displacement, if we multiply the radius we can get the linear displacements of the two ends of the spring, and if we divide torque by the this respective diameter of the two gears we can able to get the force. So basically we converted linear displacement and force for this linear spring. Now we can able to see that this particular torque, this particular force is coming from the stiffness of the spring and relative extension of the spring at two ends. So these are the relative extension. So this is one of the relation, and this relation we can able to write in terms of this. You can able to see we have written this expression. We have written phi z2 left of that, and all other terms I have taken this side. Apart from this, because there is no other force in between, the two ends of the force should be same. So this is the two forces are same at two ends, and this we have written in this form. So basically now you can able to see we have related the state vector left of 2 and other is right of 1. So this two equation 1 and 2 we can able to combine in this form, in which this is the state vector left of 2 and this state vector right of 1, and this is the required F matrix for the gear which we were interested to obtain. So once we have this, then we can able to obtain the governing equation for the whole system, because now we can able to combine these, because now we can able to see we can able to substitute this here, and so we will get, and even we can able to substitute this here. So we will get overall transfer matrix, and then we can able to apply boundary conditions. Those things we have illustrated previously. So main focus of this presentation is how to develop this F matrix for the gear pair flexibility element. Now the same gear element we will develop using the finite element method, and let us see how we can able to develop the finite element method for this finite element for this pair. So same, this is the linear displacements and these are the forces at two ends. Now we can able to see that for the spring, simple linear spring, the elemental equation we can able to write it as this is the stiffness and these are the linear displacements and these are the forces. and these we can able to rearrange in this form, so that we have angular displacements here, and so just we have rearranged this like this. There is no only 2 we have taken this side, and the same this equation we can able to rearrange in the further like this, in which even we can able to write this in the torque form. So, the angular displacement and torque form. So, once we have the elemental equation for that spring element, we can able to develop the elemental equation for the whole system. So, that means we have developed for this and the spring and this. So, element 1, 2, 3 they can be combined, and then we can able to obtain the boundary condition. So, the main focus of this illustration is that this is the elemental equation for the spring which is there between the 2 gears because of its flexibility. So, once we know this, we can able to apply the whatever the procedure we developed earlier to analyze this kind of system. So, today we developed the gear element initially with the finite element method, and through illustration we have seen that how we can able to analyze a simple gear pair or even a branch system using the finite element method. Then we took up another interesting case in which when there is a flexibility at the gear pair contact point, then how we can able to analyze such system. So, for such system we have developed the equations first using the Newton's second law of motion, then we developed the transfer matrix method for such flexibility, and even we have developed the finite element for such flexibility of the gear pair. And once we have these elements or the field matrix in the form of matrices, then we can able to easily analyze such system easily. So, with this we can able to see that especially the finite element method is very powerful tool for analyzing a rotor system. We have seen this for torsional case, but in future we will be applying similar approaches for transverse vibration, transfer vibrations also. So, in the subsequent class now we will start with the transverse vibrations, especially for the multi degree of freedom system, because till now we have considered for transverse vibration only the single mass rotor system, but we have not considered multi mass rotor system. So, in this subsequent class we will be dealing with transverse vibration for multi degree of freedom system.